Okay, so today we'll be looking at the techniques of ground improvement. So our previous topic was about ground problems. So this topic will be ground improvement to fix the ground problems or overcome the ground problem. So two most common methods for ground improvement are soil compaction or densification and soil stabilization. So we have two common methods, compaction, which is more common method, and soil stabilization. Soil stabilization can be using three techniques as well, using lime, so mix the soil with lime, okay, or mix the soil with cement, or mechanical uh, method. Okay, we will talk about this method later today in this lecture, but let's start with the compaction. What is the definition of the compaction, or what does the compaction mean? The compaction means reducing the air voids in the soil with very little or no reduction in the water content. So if you remember from our first few lecture, we know that the soil has three phases. The soil has like the blue is the soil particles, and we have another phase of the water, and the third is air. The compaction means we need to reduce the air volume of the trapped in the soil between the soil particles. Okay, so for example, this becomes the new soil. So the soil still same, the water still same. We have soil particles and water content or water uh, moisture content, and the air become reduced. Okay, so this is the compaction definition. So just need to reduce the air voids inside the soil. Okay. So what is the benefit of compaction? The benefit of the compaction is the density of the soil. For example, before compaction here, the density of the soil or the specific gravity of the soil gamma was 16 kilonewton per cubic meter. After compaction, so this is the compaction method or the compaction machine. After we will talk about it later as well. After compaction, what happened to the air? The air get out, air reduced. So we have higher density. Okay. So for example, from the density from 16, now the density after compaction become 21. So this is the main idea about compaction, reducing the air to get a higher soil density, which means higher soil strength. Okay. So this is the main concept of compaction, and we use this method to increase the soil strength or the soil depth. Okay, here is what I was talking about. So this is the soil sample, for example. This sample has three phases: soil, water, and air. What we are doing is using the compaction. We keep the soil solid or the solid particles same, water same, the air reduced. Okay, so again, sigma before is, sorry, gamma, or the density before compaction, is less than gamma of the soil after compaction. Okay, so now, or again in details, what is the benefits or what is the reason of the compaction? Why we are doing the compaction? The compaction, first benefit of the compaction is to increase strength. Okay, as I mentioned, we increase the soil density. Increasing the soil density lead to increasing the strength. Okay, because in weak soils, it may be economical to strengthen the soil than use deep foundation. As you know, if we have soil, weak soil, so we have some weak soils. For some cases, we need to use deep foundation or pile. So we have deep foundation. These deep foundation are expensive or costly. So sometimes it is better to compact the soil or strengthen the soil rather than using the deep foundation. This is why the compaction is important. The second benefit we can have after compaction is decrease the permeability of the soil. As you know, the soil particles, the water can flow between the soil particles, right? So if you make the water particles very densified, so the movement of the water between the soil will be limited or reduced. Okay, so this is the second benefit we can have, decrease the permeability of the soil or the water movement inside. Okay, so this make it difficult for water to enter or flow through the soil. The third benefit we can have is lower soil movement potential. Okay, again, when the soil particle is apart, so their movement is easier than when they are very close together. So if the soil particles are very close together, so hardly can move. Okay, so this improves the performance. First, this lowers the soil movement potential, which lead to improvement the performance of the structure above or roots above. Okay, the fourth benefit we can have is increasing the durability or increasing the stability over longer lifespan. Okay, so as a result of all these three, the top three, we can have the third one. So increasing the durability of the ability of the soil. Okay, which make it very beneficial for roots on top of the soil because roots need to be or need to live for longer, so long lifespan. Okay, so this will make the roots more durable or the structure above the soil more durable. Okay, so this was the important reason of compaction or why we need compaction. And next, what is the effect of the water content inside the soil? So as we discussed earlier, we have solid particles, water, and air. So what is the role of the water inside? effect of water inside the soil. Okay, we can have two cases. First case, if we compact when we have higher or high moisture content inside. So the first case is high moisture or high water content. The second is compaction at lower moisture content, or we have low moisture content. And which one is better? Because this will affect our compaction process. If it is better to compact when the soil has a high water level or high water content, or has low water content. Okay. So what happened at high water content? If the water is high, so easy to move the particles around as the pore water pressure is slightly negative. So if we have water between the soil particles, okay, this water will work as lubricant between the soil particles. So make it easier to move. Okay. So when we have water pressure or water content, so the solid particles will be easier to move. So it will be easier to compact the soil. Okay. But the problem is, so this is the pro. The con is lots of energy is lost in squeezing the pore water around or out of the void. Okay. Because what you need to do for compaction, you need to make the soil particle close to each other to make it more densified. So this means that you need to push or compact more or add more energy or forces to make the solids close to each other. And this energy will be lost in like squeezing the water out of the soil. Okay, so we have two parameter here. One parameter is advantage, which is the water will be lubricant to easily move the soil particles. But the disadvantage is lots of energy is lost just to move the soil out, the water out of the soil. Okay. The second case is if we have low water content. If we have low water content, we lose the advantage of lubricant, so it will be difficult to move the particles around because the pore water pressure is high negative, so we don't have any water pressure. So it will be very high to move harder, move the soil particles is harder now. Okay, this is the con in this time. What is the advantage or the pro? The pro is little or no water pressure will be squeezed around out of the void, so we need less energy is required. Okay, so the two cases are opposite. So high water pressure or high water content is the opposite of low water content. Okay, so now if you are doing the compaction at site, which case you are choosing, high water content or low water content? So if we look at this one, so this means that at particle moisture content, compaction is most efficient. You can choose you can choose one of these because both of them has pros and cons. Okay, so the best option or the best practice is we need to find the best or the optimum moisture content where the compaction is most efficient. So we will be looking at two things: the optimum moisture content and the maximum density. So to do to make the compaction most efficient, you cannot use high or low content. This is incorrect. So we need optimum moisture content. Okay. So we need to look or to find the optimum moisture content or optimum water content to do the compaction or to make the compaction efficient. How we do that? This will be done using some lab tests, okay? And we will get the result here directly. So after doing some lab tests or lab trials, we have done some moisture content like compaction. This figure comes from compaction using different moisture content. Okay, and measure the soil density gamma at each moisture content. Okay, when they did this in the lab, what they found? They found that if we draw a relation between the dry density gamma and the moisture content MC on the horizontal axis, we will have few points. Okay, if we connect these points with a curve, so this will be our curve. Where is the highest dry density? This is the point of high dry density. So if we go horizontally, so this is our higher or highest dry density. We call this is the maximum dry density. Okay, we call it MDD. Okay, so this MDD means the highest result we can get or highest soil density we got from compaction, right? So this is the highest we can get from compaction. This highest dry density MDD corresponds to one of the moisture content. This value of the moisture content is the optimum moisture content we are looking at, or OMC. Okay, if you can see what happened if we increase the moisture content more, the dry density start to the dry density reduce again. So this is our aim, the highest dry density. So we have MDD or maximum dry density happen or occurs at optimum moisture content, OMC. Okay, so if you are in the site, you are looking at the optimum moisture content to do the compaction at, so that you will get the maximum dry density for this part. Okay, if we look at this question here, why we are using the dry density as a compaction control parameter? Because the dry density is indication of the densification of the soil, and also the dry density is an like indication of the soil strength. Okay, so if you have high dry density, you have high soil strength. Okay, so That's why we are using the high dry density as the dry density as the control parameter. Okay. Do you have any question, Dylan? Okay. So now we know that the compaction need to be done at the optimum moisture content, and they have done some tests to find what is the optimum moisture content. So let's now talk about the laboratory test for compaction in details. What is the purpose of this test? To determine the proper amount of mixing water to be used and resulting degrees of density. So this means again the moisture content and the corresponding dry density. Okay, so the result of this test will be similar graph as we got in the previous slide, dry density versus the moisture content. And again, here is the maximum dry density, and here is the optimum moisture content. Okay, what are the tests we have? What are the tests we have for compaction? Two tests, standard Proctor test or standard compaction test, AS 1289.5.1.1. This is the test closed. The second test is the modified Proctor test, AS 1289.5.2.1, which is the modified compaction test. So we have two type of compaction test. One is called standard and one is modified. Let's see what is the difference between the two tests. So the standard and modified test has almost similar apparatus. apparatus. So we have this apparatus to do the standard and modified test. Okay, so we have hammer and we have this bowl. Okay, so for the standard test, the mass of the hammer is 2.7 kilogram. The height of the drop is 300 millimeter. Number of soil 3. Blow uh, or the hits per each layer is 25. The energy is 596. So what does this mean? This means if we have, this is the power. So the soil in the Proctor test, in the standard Proctor test, need to be as 3 layers. Each layers need to be blown 25 blows. Then you put the other layers. Then you put the third layer. Okay. So this means 3 layers. Each layer 25 blows. Okay. The height of the drop of the height of the hammer drop is 300 millimeters. So you need to drop the hammer from this height. The hammer weight in the standard Proctor is 2.7 kilogram. So you will drop 2.7 kilogram from 300 millimeter over the layer for 25 below. Then add the second layer, then the third layer. The energy equivalent or the energy generated in this test is only 596. Okay, what is the difference in the modified? The modified test means it was standard, but some they have done some modifications to it to have different or modified results or modified or better results. So the hammer weight in this case is instead of 2.7, it is 4.9. The drop height is 450 millimeter. Here the number of layers is 5. So we have 5 layers instead of 3 layers here. Okay. Still the number of belows for each layer is 25. But here the advantage we got is we have more energy generated in this test, or more energy needed in this test. Okay. So the energy in this test is 2703 kilojoule per cubic meter. Okay. So this is the two tests we can have, standard Proctor test and modified Proctor test, to find the optimum moisture content and the maximum dry density for types of soil. Okay, so these are some results or some graphs for the OMC and MDD for different type of soil. OMC again, optimum moisture content. MDD is the maximum dry density. Okay, if you look at this curve, so we have here dry density on the vertical axis or gamma, and moisture content or water content MC on the horizontal axis. If you look at this test, for example, soil number 1 is a well-graded sand. So it is well-graded soil. That's why the dry density of this soil is high, almost to 1.8, 2.18. Okay, and this is the corresponding moisture content, almost 7. Okay, and so on for each type of soil. This is the optimum MD, and here is this is the optimum MD. Sorry, this is the maximum dry density MDT. Okay, so the first soil is well graded loamy sand because it is well graded, so that's why we have dry density. If you go down, or if we go with the curves in this direction, what happened to the dry density? So the dry density decrease because the soil grade is low. So that's why the dry density increase. And also, if you have a look here, so when the dry density decrease, what happened to the moisture content increase? So the moisture content increase. Okay. And if we look at the last one here, poorly graded sand. So also the poor graded sand or the uniform distributed particles size sand. This means that the sand particle size is almost same. Sorry. So we'll need to repeat this part again. So what is reaction we'll get from the standard and modified Proctor test? Standard and modified Proctor test. We'll get some graphs between or relations between the dry density gamma and the water content or moisture content density. Okay, these graphs are the OMC and MDD for some different soils. So, for example, if you look at the first one, well-graded loamy sand, this soil has 88% of sand, 10% of clay of silt, 2% of clay. If you look at this curve, the first one, so this curve has MCC is this value, MDD, sorry. So MDD for this soil is almost 2.18 or 2.17. Okay, and this is the optimum moisture content, OMC, is something like about 0.7, 0.5 or 7. Okay, so for each type of soil, we can have the maximum dry density and the optimum moisture content and so on. Okay, so if we look here, when we go down, the soil become weaker, so we have less or reduced dry density. As you can see here, if you look at the curve, when we go in this direction, the soil dry density decrease or reduce. Okay, and what happened to the water content or moisture content? If you look at the moisture content in this direction, so the moisture content needed is higher. So moisture content is higher. Okay, and if we look at this soil type, the poorly graded sand, the poorly graded sand means uniform. Poorly graded sand means uniform size of particles. So this means that all the size particles are almost same size. Okay, this means or this indicates that the compaction or the compaction of this soil will not be effective because the soil particles are same size. If the soil particles has different sizes, so it can be easily compacted. That's why the polyglot cell or curve number 8 has very low maximum dry density because it is hardly compacted. If we look also at this curve, if you look at this line, what does this line indicate? This is the limit of the soil moisture content because this line indicates the zero air voids in the soil. So this is theoretically or theoretical value, not actual value, because again, if we have soil, so we have solid particles, we have water, and we have air, right? So this air, it is impossible to make it zero in real life or in practice. So this line cannot be reached. That's why all the graphs, if you can look at this graph, all the graphs cannot be close to this edge line. Okay, so this is the explanation of this graph and some values of OMC and MDD got from the standard and modified process. Okay, let's have a small example or a small practice here for compaction and OMC MDD for some different soil. We have three graphs, A, B, C, and here is the dry density of the soil. okay, or gamma drive. And here we have the moisture content MC. Okay, so we need to know which material is represented by each curve, by which curve. Okay, so for example, if we look at the MDD for each soil, which one has the higher MDD? This is highest MDD, so this is a MDD. So this MDD 2.1. So fine crushed soil is soil number A. The second one is 2.06. So this is 2.06. So this soil is soil number B. Okay, and the third one, clay. If you look at the clay, so the clay is almost 1.89. So clay is soil number C. Okay. So again, in this direction, when we go down in this direction, so the dry density reduce. And if we look at the corresponding moisture content, if you look at the corresponding moisture content, so when the MDD high, we have low M moisture content. Okay, so for example, if this increase in this direction, so this increase in this direction. So the relation between MDD and OMP is reverse. Okay, because again, if we look here in this curve, this is soil number A. So this is the moisture content of soil A. This is the moisture content of soil B, and this is the moisture content of soil C, and this is the increase of moisture content. Okay, and this note, keep in mind that the material with higher granular particles or large particle size, we have like sand and gravel, have higher MDD and lower MC. So sand and gravel have high MDD and lower OMC. So for clay and silt, which doesn't have granular, so it has lower MDD and higher OMC. Okay, so this two, just keep these two notes in mind for the moisture content and the dry density. Okay, so this also again another small practice about the compaction and the water content for the energy effect of standard Brockton test and modified Brockton test. If you remember, when we just few slides ago, we have these two tests. Which one has higher energy for these two tests? The modified Brockton test has higher energy. The standard Brockton test has lower energy. So if we go back, so this is two graphs to identify which curve is done with which or made using which test. Okay, so if we have test A and or material A and the material B, or test A and test B, so test A has higher MDD and lower OMC. This test has higher OMC and lower MDD. So test A, standard Proctor test, has OMC higher. So this means that test A is done by modified Proctor, test B is done by standard. So test A, modified Proctor, test B, standard Proctor. Because standard Proctor has higher OMC and lower MDD. Modified Proctor has lower OMC and higher MDD. Okay, so generally in modified Proctor test, we have higher combustion energy on the same material, produce higher MDD and lower MCC. Okay, so again for modified Proctor, we have higher energy because it produces higher MDD and higher and lower OMC. Okay, so this is comparison between two tests for same material. Now, for the field combustion, we have three basic soil group or classification of soil regarding or based on combustion. So based on combustion of the soil, we have three basic group or three classification. The first classification is cohesive soil. So we have cohesive soil like clays, which is plastic when wet, safe when dry. So the cohesive soil or mainly clays are plastic when wet and safe when dry. This cohesive soil need proper water content and evenly distributed over the soil is critical for proper combustion. So to have a proper combustion, you need proper water content and evenly distributed over the soil. And usually the combustion happens or achieved by kneading. Okay, how this combustion happens? If you look at this two photos, two images, this is the rollers used for clay soil. The main idea of using this roller that it has like called sheep foot. Okay, so this sheep foot rollers are used for here are used for clay soil. Okay, why this roller has this sheep foot? So we have some small deformation in the roller. So this make the area the area of the applied pressure and soil small so that we increase the pressure on the soil. Okay, so this small foot used for increasing the pressure on the soil because the clay soil needs more pressure to be compacted. That's why we need to use this type of roller. The second type of soil or the second group of soil is the granular soil, which indicates or includes gravel and sand, which are cohesionless soil. So we have cohesive soil in group one and cohesionless soil in group two, which are stable above the water table. In the conduction, we need here much water is needed plus mechanical energy. So for the granular soil, because it has big size of particles, so we need more water and more energy. The energy will come from the roller. So we have vibratory roller and the multi-tire roller. These two types of roller used for soil combustion or mainly granular soil combustion. And this one, the combustion usually achieved by the vibration. So we apply apply vibration. The vibration will cause the soil particles to rearrange. Okay. So for example here, if you apply the vibration, for example this vibrates. So what happens to the soil? The soil rearrange again together to become more compacted. Okay. So this is after the vibration. Okay. So we have two types of soil now. The third one is the organic soil. Organic soil is not good soil because it is very weak soil. Okay, and has low strength, so you can't structure any building or road on it. So it is very weak, so that cannot like uh, carry any structure or any load on it. So what we need to do is just removing this soil and replace with like granular or strong soil. Okay, so this soil is very weak and cannot be used for any type of construction and need to be replaced. Here is some other combustion equipment we can have on site for some narrow areas. For example, we have this vibration plate. Again, it applies vibration to the soil layer, so it can be used for granular soil. This also as well is called Walker plate, so it is same applies also some vibration for trenches or narrow areas again. And we have this trench roller which is controlled remotely. Okay, and if you can see, it has also some of the heat foot bars. So this can be used for cohesive or clay soil. Okay, so these are some machinery or equipment used for compaction. And here in this table just need to have a look at it. Don't need to memorize it. You just need to know what is the best equipment for which soil and what is the application. So we have the equipment, we have the most suitable soil and the application of this equipment and what is the soil that is not preferable to use this machine for. So for example, we have smooth wheel static, wheel rollers, static or vibrating. This is good for well-graded sand and gravel, cracked rock and asphalt because this is applied vibration. So the vibration is good in the well-graded soil. We have also rubber tired rollers, grid rollers, and sheepfoot rollers. Sheepfoot rollers, we have two things under it. We have vibrating plates, dampers and drummers, and back rollers. So each machine or each equipment has its most suitable soil and applications. For example, again, if we look at the first one, so we have the typical application is running surfaces, base courses, subgrades for roads and runways. So it can be used for roads and sub runways of the airports. And least suitable soil, it cannot be used for uniform sand. Okay, so you can have a look on it. So if you have like a type of soil you need to compact, you need to refer to this table to find what is the best equipment to use. Okay, and here is some other compaction equipment which are used in some special events or special cases. Okay, here for example, it's called the impact roller, and this one is deep dynamic compaction. These two are used for compaction of deep soil more than 2 meters and up to 10 meters. Okay, because if we return back to all this type of equipment we have used, all this type of equipment are used for shallow or thin layers of soil. Okay, so this can be maybe used for only 300 millimeter depth of soil. Okay, but if we are in this case, for example, need to have very deep layers. For example, we need to like compact this layer, which is like 3 meter or 4 meter deep. So if you apply the roller, if you apply the roller, so this roller will not be sufficient to compact this layer. So what is the best option to do this layer is one of these two machines, the impact roller and the deep dynamic compaction. So now I will just show you an example of that. Okay, so you can have a look on one of these videos. Okay, guys. Okay, then can you hear me now? Have you watched the video? Do you have any question about the video? So this type of like compaction equipment or rollers are very heavy and apply higher energy to the soil so that they can reach deeper burn. Okay, we can also have a look on the other one. So have a look. Okay, so these are two type of compaction for deep and far layers of soil, impact roller and dynamic compaction. Okay, we have another technique. It's called vibro flotation. This vibro flotation means, so just briefly explain it. So what we are doing is just like digging a column or a hole like a column. Okay, and then in this all, they had better or stronger soil. Okay, and using this vibro floating equipment, which is spraying some water inside as well. So this will stabilize more soil, and that's why it's called. This soil can be, sorry, this soil can be sand. That's why it's called viable sand column or stone. So it can be called as viable stone column. Okay, this also technique is used for deep layer compaction or improvement. Okay, we can have a look also on this video. Okay, so this is the vibro flotation or vibro sand column, and also the techniques to use the deep layer compaction. Okay, and this the next is how we field control, or how we control the compaction in the field, or how we know that we reach the optimum or the required density of soil after compaction. Okay, so there are three methods: the sand cone method, balloon method, and oil or water method. All of them have almost similar idea. The idea here, for example, if we look here, so the idea is we dig a hole in the soil. So we dig a hole in the soil and we have some sand in this jar. Okay. The problem is we don't know the volume of this hole. So what we are doing is we got a sand. We know the gamma of this sand or the dry density of this sand. The dry density of this sand is equal to the mass of the sand over the volume. Okay. So what we will do is open the valve here. So this will make some sand drop here. So when the sand drop here, we will weight the mass of the sand. So the mass of the sand will be known for us, and gamma dye for this sand is known for us. So we will get the volume of the sand. The volume of the sand will be equal to the volume of our soil. Okay, so for our soil, what we will do is we need the density of this soil. So the density of this soil will be the mass of the soil. We can weight it or can get the mass of it divided by the volume of sand. So now you can know gamma soil and you can know if the maximum dry density required is reached or not. Okay, so these methods are just to find the mass after compaction. Sorry, the density after compaction. Okay, so all the methods are almost same idea. So you have a hole and you want to measure the volume of this hole by using the sand or the balloon or the oil. Okay, so this is called field control method. There are another method which is nuclear density meter. So this method is a bit not very common because it needs trained and licensed workmanship because it is nuclear. So the man who would do the test would be under some radio effect. So you need to wear some special equipment. So the idea is we have some detector somewhere, detector machine, and we have this tool to embed in the soil or push in the soil. So this will be the source of the radio rays. This radio rays will have some passes through the soil until it reaches the detector. Okay, so this gamma radiation is scattered by the soil particles, and the amount of scatter is proportional to the total density of the soil. So the gamma radiation have some relation to the density of the soil. Okay? So based on the reading in the detector, we can find the density of the material. Okay. Also, the water content in the soil. Again, this software crash again. Okay. So this is a real life of a real photo of the nuclear density meter. Okay, as you can see, this is the detector of the gamma radiation. Okay, so this is also can be used for field density control after combustion. Okay, now we have a look at example of minimum dry density ratios. So again, if we look at compaction test or compaction curve, the compaction test gives us a relation between the water content and the dry density, right? So we can have some few points, okay? And if we connect them with some curves, so this is our curve for compaction. The highest value you can get for this compaction is maximum dry density MDD, and is is equivalent or corresponding to the optimum moisture content. So from compaction test, we will get MDD, max dry density, and OMC or optimum moisture content, right? So in some cases, the optimum moisture content is very hard to obtain on the site. That is why there's some like suggestion or some recommendation to maybe we can use LS MDD or AIM LS MDD, which is for example 0.95 from MDD. So in some cases on site, we can target like 95% of MDD rather than 100% of MDD because of difficulties on site. Okay, so if we have this new percent, so if you look at the curve, so we have new 2 points. These 2 points will give us a range of optimum moisture content. So we are not strict on one moisture content or optimum moisture content. So we can have a range between these 2 points. Can use any moisture content between these 2 points. So this make it easier on site. Okay. In this section, we give some recommendation about what is the target MDD for some selection. For residential load fill, we can target 95% of the relative standard compaction. For higher loaded fill, we can aim up to 95% relative standard compaction. For pavements, we need 95% relative to modified compaction. This guidance or this information can be found in AS 3790, 3798 section 5. Okay, so this is just some recommendation to make it easier on site. Okay, so some of the economics we need to have a look at with combustion. So also this is only not only engineering or like geotechnical problems. Somehow we need to look from the economic point of view. So the fill is usually paid for based on the blade fill volume. So the fill also used for combustion is not free, so you pay for it. Excavation, excavation and hauling are often paid for based on the insight of volume. So also the excavation and hauling of the soil is paid for. These are normally different volumes depending on the material. So the volume of the material also change. Volume of material play some role here. So you don't have to get caught in the middle. You need to have other thinking. Volume is also affected by moisture of the material. So the volume of the material can be changed due to transportation, due to hauling first, and transportation, and also due to moisture content. Okay, so this also the change in volume will affect the payment of the film or the payment of excavation and hauling. Okay, so that's why we need to be careful when we do the combustion. And this is an example of the points we mentioned earlier. So, for example, if you need 1 cubic meter of soil, okay, and we will pay something for it, like for example, $100 for it. So, if you like excavate 1 meter, 1 cubic meter, which is 1.8 meters, when you haul it, so after due to the movement and the soil, the moisture content in the soil, the volume increased to, for example, 1.8 meters. Okay. Then when you try to put it in the final location and try to compact it, you found the volume is decreased to 0.85 cubic meters. So you need 1 meter, 1 cubic meter, and you only got 0.85 meters. So you lose around 15%, and also you have paid for fill, for excavation, and the haulage. Okay, so this one example. Another example, if you have like granular soil or rocks. So for example, if you dig or move 1 cubic meter and you try when you haulage it on the truck, this volume become 1.6 meter because the rock soil particles are very large, so they rearrange. So when they rearrange, the volume increase. Okay, so when you try to compact it, for example, if you compact it and you make it 1.4 cubic meters, so you still have gained 40% of the volume. Okay, so some cases you will lose soil, some cases you will gain more soil, and in each of them you will be costed money, extra money. So you need to avoid this. Okay, so that's why we need to in some cases we need to find another solution to improve the soil, which is soil stabilization. So soil stabilization is alternative of combustion. In some cases, we cannot do the combustion, so we need to do the soil stabilization. Why we need soil stabilization? Because it enables the soil on site which are not suitable as they are found inside waterlogged or weak. So in some cases, the water in the soil in situ is weak or not suitable for construction. So what you can do instead of compaction, you can do the soil stabilization. And this technique, the soil stabilization, is more cost effective than import of higher grade material for compaction. Okay, what is the benefit from associated with soil stabilization? One, soil cost benefits, less excavation and dumping cost, less transportation cost, less construction time, and thinner pavement. So all these are cost benefits or effectiveness of the stabilization. The other criteria or other dimension of the benefit is the environmental benefit. Reduction in the transportation, so this will reduce also the CO2 footprint. Also reduction of the landfill resources. Again, less footprint because less use of binders. Reduction in requirement of the quarried stone. So you don't need to use natural quarried stones. So will also this make some like good effects on the environment. Okay, what is the soil stabilization do for the soil? It improves the strength, improves the permeability, improves the durability, improves the volume stability of the soil. So this increased strength, which is our main target. So this is our main target we are looking at is the strength, and also increasing the durability is good for, as we mentioned earlier, roots. Okay, so these are some benefits of the soil stabilization. What are the methods of soil stabilization? We have mechanical stabilization, so we can mix one or two, sorry, mixing of two or more soil types. This is called mechanical stabilization. And also we can have another type which is cement stabilization. The cement stabilization is used for granular soil. So in granular soil, we use cement stabilization. So it's like quite similar to concrete. So this makes it stronger and better bearing capacity. So we need to add like 2 to 3% of cement by volume mixed with soil. Okay. The third is lime stabilization. Lime stabilization is used for clay soil to quickly dry out with soil because, as you know, clay soil has higher moisture content. So the lime is very sensitive to water. So when it mixed with water, it becomes very it fit up quickly and dry early. Okay, so this will reduce the plasticity of the soil and increase its strength and provide impervious layer. So for lime, we need to add 2 to 5% of lime by volume of the soil. Okay, and don't forget that we all this need to use water. So adding cement or mixing with other soil or adding lime, we need to add water. Okay, you can have a look on these two videos about lime stabilization and cement stabilization for soil. Okay. And here is example of the process of lime stabilization. As you can see, this truck or this tank will spread some lime on the soil. This machine will mix lime with the soil, okay? And this machine is the foot sheep roller. As we mentioned, this is clay layer, so we need the foot sheep layer to compact. Then we have a grader to grade the surface to make it even. Then finally we have the smooth roller to final compact or final finish of the soil. Okay, so this is the process of the lime, adding lime to the soil. And these are some real photo of the soil stabilization equipment. As you can see here, this is the lime tank, and this is the lime, and this also another like small tank. Okay, so this is just some real photos, and again also some of the photos. So this is the lime, and as you can see here, this is the deep foot roller. So all this equipment are used for lime stabilization, and that's it for this lecture. So the next will be pavement. Thank you.